All right, let's get into it. Today, we're going to look past the slick tires and the fancy carbon fiber and dive deep into the strategic heart of a world-class electric race car, the high-voltage battery. And look, this isn't just about packing in some cells to store energy. This is about forging a competitive weapon from the ground up, using world-class engineering strategy. So let's start our breakdown. You see this quote? This right here is everything. It's the core philosophy that separates the teams that just show up from the teams that actually win. I mean, anybody can build a battery that makes a car move, but the elite teams, they build one that makes the entire car faster, handle better, and even safer. It's a total mindset shift, and honestly, it's the first thing you have to nail if you even want a shot at the podium. Okay, so for the next little while, let's put on our senior powertrain architect hats. We're going to take a real McKinsey-style approach here and break down exactly what it takes to engineer a battery that wins championships. We're basically opening up the strategic playbook that the very best Formula student teams use to get that critical edge. So, first up, we're talking about our first course strategy, and it's a bit of a weird one. It's all about an aggressive, almost counterintuitive weight limit. We're not just trying to be light. We're trying to win the race before the car even sees the asphalt, simply by subtracting mass where most people wouldn't even think to look. And here it is, the number that changes the whole game, 6.0 kilograms. This is the absolute maximum weight we are allowing for a single battery module. Now get this, the official rules, they'll let you go all the way up to 12 kilos. So why are we cutting that in half? Well, this isn't a suggestion. It's a non-negotiable, internal law. It's a super aggressive decision that, right off the bat, completely separates your design philosophy from 90% of the field. Okay, so you're probably thinking, why? Why make your life so much harder with a limit that punishing? Well, because that number isn't just pulled out of thin air. Hitting it unlocks this whole cascade of strategic advantages that affect everything from vehicle dynamics and safety all the way to how fast you can work in the pits. Okay, first up, vehicle dynamics. Lighter, smaller modules mean you have way more control over the car's center of gravity, and even more critically, its yaw inertia. This isn't just about being a little quicker in the corners. It's about building a car that's predictable and responsive right at the absolute limit. That's what gives your driver the confidence to really push. Second, safety. Look, the physics here are just brutal. In a 40G crash, a 6-kilogram module is going to exert about 2,300 newtons of force. A 12-kilogram module? Double that. Lighter is just fundamentally safer, plain and simple. And finally, something a lot of teams forget, pitlane efficiency. A 6-kilogram module is a one-person job. That makes repairs and swaps incredibly fast. It's literally like hot swapping a hard drive in a server rack. In a long endurance race, that speed can be the difference between finishing on the podium or not finishing at all. And this is where the real engineering nightmare, or challenge, depending on how you look at it, begins. Almost 80% of your 6-kilo budget is already gone. It's locked up in the cells themselves. You can't change that. Which means every single other component, the frame, the cooling plate, the electronics, the bus bars, has to be crammed into that little sliver of what's left, just over 20%. So what do? You start counting every single gram. We're talking about just 1.23 kilograms for everything else. This is where you're forced to get exotic. The frames, you're not molding them, you're 3D printing them from carbon fiber reinforced nylon. The bus bars? Forget heavy copper, you're laser welding aluminum. The cooling plate is a paper-thin microchannel aluminum piece. Every single choice here is a tough trade-off, balancing weight, cost, and just the ability to actually make the thing, all to stay inside that razor-thin margin. Okay, so we've obsessed over weight. Now let's switch gears and talk about the electrical architecture, because how you approach weight completely shapes how you handle the power. And in this world, the name of the game is pushing for max power and efficiency while trying to navigate a minefield of really strict rules. It's a balancing act that creates this fascinating paradox. You know, when it comes to the cells themselves, for a top-tier team, there's really only one option on the table: high C-rate lithium polymer, or LiPo, pouch cells. C-rate is just a fancy way of saying how fast a battery can dump its energy. The higher the C-rate, the bigger the punch. These pouch cells deliver insane power. Their big flat surface is perfect for cooling, and their brick shape means you waste almost zero space. From a strategy standpoint, it's a slam dunk. The case is closed. But of course, making the right choice immediately creates a brand new, massive problem. So for efficiency, you want to run a high-voltage system. Let's say we design one with 144 cells all linked together. The math is easy. 144 cells, each charging to a max of 4.2 volts, gives you 604.8 volts. And the problem? The rules have a hard, unbendable limit of 600.0 volts. And if you roll up to scrutineering with that, game over. You're instantly disqualified. All that work for nothing. So how do you fix it? The solution is just beautiful. It's elegant. It's called voltage capping. All you do is program your battery management system, the BMS, to stop charging each cell just a tiny bit below its absolute maximum, say at 4.16 volts instead of 4.2. That tiny change brings your total system voltage right under the 600-volt limit. Yeah, you give up a tiny fraction of your total energy, but in exchange, you get to keep your super efficient high-voltage design and be totally legal. This is a classic move of a top engineering team, using clever software to get around a hard physical limit. All right, next big decision, how much gas do we actually put in the tank? Or, energy in the battery. We call this finding the golden interval. It's that perfect sweet spot between performance and endurance. You run the numbers for the 22-kilometer endurance race, and you figure out you need about 6.6 kilowatt hours. So the optimal zone, your golden interval, is between 6.8 and 7.2. That gives you a nice safety buffer. If you go below that, you risk running out of juice before the finish line. And if you go above it, you're just lugging around dead weight that's making you slower on every single lap. Okay, let's shift focus to something absolutely non-negotiable: safety. The box that holds all these cells, the accumulator, it can't just be a lightweight box. It has to be a fortress, an absolute fortress designed to handle the unbelievable forces you'd see in a high-speed crash. The numbers here are just staggering. The rules say this container has to survive a 40 G impact. And for a battery this size, that works out to a force of 21,582 newtons. That number is huge, and it dictates every single decision you make about the structure. Now, what does that even mean? To put it in perspective, that's like taking a small SUV and balancing it on its side, right on top of your battery box. The structure has to take that entire load without bending or breaking in a way that could threaten the cells inside. It's an incredible challenge. And that's exactly why your choice of material is so critical. I mean, just look at this comparison. Carbon fiber reinforced polymer, CFRP, is the only way to go. It's 3 times stronger than aluminum for the same weight, and it's a natural electrical insulator. Honestly, from a strategic point of view, it's not even a debate. Any team that's not using carbon fiber for this is already making a huge compromise from day one. So how do you actually build this fortress? Well, there's a blueprint, a kind of recipe for success. You build a sandwich panel using a super light, super stiff core, like Nomex honeycomb. You lay up your carbon fiber sheets in different directions so it's strong from every angle. And anywhere you have to bolt something to it, you embed little metal inserts so you don't crush the carbon fiber. And then you have to prove it works, with both computer simulations and by physically breaking test pieces. Okay, for our last deep dive, let's talk about 2 things that can kill a project instantly: heat and leaks. This is all about mastering thermal and fluid management. You have to get rid of the incredible amount of heat these cells produce, and you have to be absolutely positively sure your liquid coolant never ever leaks. So pouch cells have this weird quirk. It's called breathing. When you charge and discharge them, they literally swell up and shrink just a little bit. And if you just clamp them down tight and don't let them breathe, you'll crush them from the inside out. That can lead to serious damage and even thermal runaway, which is, bad. The fix involves using special foams that compress and designing your cooling plates to float a little so they can move with the cells. All right, let's talk leaks, because coolant and high-voltage electricity are a catastrophic mix. There are basically 2 main philosophies to make sure that never happens. The absolute gold standard is continuous tubing, one single unbroken pipe that snakes its way through every module. It's a nightmare to build, but it means there are physically 0 connection points inside the box that could leak. The other way is to use these fancy double-sealed connectors that have a little weep hole to safely drain away any fluid if the first seal fails. The choice really comes down to what your team can actually build and how much risk you're willing to take on. So when you pull back and look at all these pieces, what do you see? It's not just a random collection of engineering choices. A clear playbook starts to emerge. It's a whole system of interconnected decisions where every single choice supports the others, all driving towards one goal. And really, it all boils down to one core belief. This phrase says it all. The race, it isn't won on Sunday afternoon on the track. It's won months, maybe even a year before, right there in the design office.
When you make these smart, aggressive, strategic choices from the very beginning, you're not just engineering a car to be fast, you're engineering it to be tough enough to actually finish the race.
And that just leaves us with one final question to think about. Everything we've talked about today, that's the playbook for a top team right now. So the real question is, in a sport where you're fighting for milliseconds, where is that next big advantage hiding? Because you can bet the best teams are already looking for it. Thanks for joining me on this deep dive.